rest now, let your body grow calm, and let the quiet gather around you. For a little while, we'll drift slowly through the distant galaxies our own quietly draws in. When this helps you sleep, subscribe. I add a new one every single night. On one side of a dwarf galaxy, the pull of gravity is stronger than on the other side. That difference is small. Across a distance of a few thousand light years, the difference in the force exerted by a massive galaxy nearby amounts to a gentle, almost imperceptible gradient, a tug slightly harder at the near edge, slightly softer at the far edge. The same basic fact of differential gravity that raises tides in an ocean, now operating across tens of thousands of light years of stars and gas and dark matter. The geometry of it is precise. The near side of the small galaxy is drawn toward the large galaxy a little faster than its center, and the center is drawn a little faster than the far side. And because of that difference, because of that steady gradient, written into the fabric of how mass attracts mass across space, the small galaxy is not simply moved, it is stretched. This is where the story of a consumed galaxy begins, not in collision, not in fire, but in a difference so gradual it would take millions of years to measure with the eye. A slow elongation along the line connecting the two galaxies, a compression along the axes perpendicular to that line, the whole small structure being gently, inexorably deformed by a force it cannot resist and cannot escape. The stretching is quiet. There is no sound in the space between galaxies, no tremor that propagates through any medium, only the steady geometric fact of gravity acting across a distance, and the slow response of stars and gas and dark matter to the uneven terrain of the gravitational field they are moving through. The dwarf galaxy continues to orbit, it continues to rotate, its stars continue to burn, and all the while along its outer edges, the differential pull is working, drawing the loosest material, the stars farthest from the dwarf's own gravitational center, the ones held most weakly by their home, outward and away, the way a current draws sediment from the edge of a riverbank, grain by grain, without urgency, without pause. Gravity does not hurry. This is perhaps the most important quality of the process, its absolute patience, its indifference to any time scale shorter than millions of years. The stars in the outer regions of a small galaxy are like grains of salt dissolved at the rim of a pool, and the tidal forces of a larger nearby galaxy are like a slow current moving through that pool, carrying individual grains away, not all at once but steadily, one close approach at a time, each orbital passage surrendering a little more material to the larger structure. The astronomers who first modeled this process numerically in the decade of the 1970s ran simulations on computers that would today be considered primitive, watching numerical point masses respond to equations of gravitational dynamics. And what they saw was not dramatic, it was slow, it was geometrically elegant, and it was, they understood, universal, a process that must be happening everywhere in the universe, that a small galaxy orbits a larger one, which is to say almost everywhere, which is to say throughout the enormous and ancient structure of the cosmos. The technical term for what happens to a small galaxy in the gravitational field of a large one is tidal disruption. The force responsible is the tidal force, and it operates in exactly the same mathematical way as the tidal force that deforms the Earth's oceans as the moon passes overhead, scaled up by a factor that staggers any ordinary comparison. The Earth's ocean tides are raised across a planet roughly 8,000 miles wide. The tidal forces that shape a dwarf galaxy operate across a body that might span 30,000 light years from edge to edge, a distance so large that light traveling at the fastest speed anything in the universe can travel would take 30,000 years to cross it. And yet the mathematics is identical at both scales. The body closer to the source of gravity is pulled a little harder than the body's center, and the body's center is pulled a little harder than the far side, and the difference between those pulls is the tidal force. What it does to an ocean, it does to a galaxy. It stretches. Each time a small galaxy swings close to the larger galaxy, it orbits. And these orbits are often long, sweeping paths that carry the satellite out to enormous distances before pulling it back in. That closest point of approach concentrates the tidal force. The stretching is strongest there. The outer stars are pulled most dramatically at that moment, some of them crossing an invisible threshold, beyond which the small galaxy's own gravity can no longer hold them. They escape, not violently, not at high speed relative to their former companions, but gradually, drifting free of the galaxy that made them and taking up independent orbits around the larger host. This moment of closest approach has a name, a pericenter passage, and it marks the point at which the consumed galaxy gives up another thin outer shell of itself. The first passage strips the loosest stars, the second passage strips more, the third strips more still. Over billions of years, over billions of years, over dozens or hundreds of these approaches, the dwarf galaxy is reduced from a coherent bound structure to a remnant of its former self, its outer regions long since surrendered to the halo of stars that surrounds the larger galaxy, its core still dense but diminished, still orbiting, still slowly giving way. The stars that escape during each pericenter passage do not scatter randomly. This is one of the deepest beauties of the process, and one of its most useful properties for astronomers trying to read the history written in the sky. A star that escapes from the near side of a dwarf galaxy, the side closer to the large host, moves slightly faster in its orbit than the dwarf galaxy's center, because it sits a little deeper in the host galaxy's gravitational field and so requires slightly more orbital speed to maintain its path. It pulls ahead over thousands of years, over millions of years. This star and all the stars that escaped with it from the near side migrate ahead of the dwarf in its orbit, forming a curved ribbon of stars that arcs forward, leading the way. The stars that escape from the far side of the dwarf move a little more slowly than the center, and they fall behind, trailing in a second ribbon that curves away in the opposite direction. Together, the two ribbons form what astronomers call a stellar stream, one leading tail stretching ahead of the dwarf in its orbit, one trailing tail stretching behind, the two of them together tracing a great arc across the sky, a luminous echo of the orbit the dwarf itself has been following. A stellar stream is one of the quieter forms of structure in the universe. It does not shine brightly. It is not a nebula blazing with ionized gas, not a cluster dense with gathered light, but a thin scattering of stars distributed along a path that might span tens of thousands of light years. The individual stars, so widely separated that the stream itself is nearly invisible against the background of all the other stars in the sky. To find one requires either a great catalog of stellar positions and motions, a map of the sky detailed enough to notice that certain stars, separated from one another by enormous distances, are nonetheless moving in the same direction at the same speed along the same arc, or an image deep enough and wide enough to reveal the faint statistical excess of stars along the stream's path against the empty sky around it. Neither is easy. Both require patience and precision and the accumulation of data across years or decades. But when a stellar stream is found and traced across the sky, What it reveals is not merely the current location of a cluster of stars. It is the preserved path of a galaxy that may no longer exist, the orbital history of an object that has been coming apart for billions of years, written in the positions of the stars it has left behind. The orbit itself is encoded in the stream's geometry. The stream follows the path the dwarf galaxy has been traveling, gently modified by the complex gravitational landscape of the host galaxy's interior, but broadly tracking the same great arc that the dwarf traces in its motion. Where the stream curves, the orbit curves. Where the stream fans slightly wider, the dwarf was spending more time moving more slowly through the epicenter, the farthest point of its orbit, where things slow before falling back inward. Where the stream narrows and densifies, the dwarf was moving faster, compressing the time between moments of escape into a tighter thread of stars. The stream is not just a ribbon, it is a record. It carries the history of the dwarf galaxy's motion, its orbital inclination relative to the host galaxy's disk, the shape of the orbit, the rate at which the orbit is slowly decaying as the dwarf loses mass, and as dynamical friction, the gravitational drag exerted by the host galaxy's own structure on the satellite moving through it, gradually draws the satellite inward. All of that information persists in the positions and velocities of the escaped stars, waiting to be read by anyone with a sufficiently detailed map of the sky. Surrounding every galaxy, and every dwarf galaxy embedded in orbit around a larger one, is a vast structure that emits no light at all. It cannot be seen directly. It does not interact with the photons that carry all the information astronomers normally work with. It reveals itself only through the gravitational influence it exerts on the visible matter moving within and around it. The way the stars in a small galaxy move faster than they should, if only the visible stars and gas were present. The way the rotation curve of a large spiral galaxy stays flat at large distances from the center when it should decline. This invisible structure is the dark matter halo, and it is, by mass, the dominant component of every galaxy in the universe. In a large galaxy like the Milky Way, the dark matter halo extends hundreds of thousands of light years beyond the visible disk of stars, vast and spherical, and smooth and utterly transparent to light. In a small dwarf galaxy, the dark matter halo is proportionally even more important. The visible stars may constitute only a tiny fraction of the total mass, the rest being dark matter extending far beyond the region where any star shines. When a dwarf galaxy is gravitationally captured by a larger host and begins the long process of being absorbed, its dark matter halo does not remain separate for long. The tidal forces that strip stars from the outer regions of the dwarf also strip dark matter from the outer regions of the dwarf's dark matter halo. The stripped dark matter, like the stripped stars, forms its own extended tidal tails, though these tails carry no light and cannot be seen. They merge into the surrounding dark matter halo of the larger host galaxy, contributing their mass to the diffuse, invisible structure that pervades the enormous volume of space the larger galaxy occupies. With each pericenter passage, more dark matter is transferred. Over billions of years, the dwarf's dark matter halo is steadily depleted, its mass added to the host's, the boundary between the two halos dissolving until no boundary remains, until what was once a separate dark matter structure is simply part of the larger one, as indistinguishable from it as a drop of water dissolved in a deep and quiet pool. This is the architecture of galactic absorption when seen whole, not just the shining stars that form visible streams across the sky, but the vast invisible transfer of dark matter from one halo to another, the gradual erasure of the dynamical boundary between the absorbed and the absorber, the slow equalization of mass across the extended dark structure that underlies all visible galactic form. The stars are the record. The dark matter is the body of what is being transferred. Both processes happen together, inseparably, over the same immense timescales, and both contribute to what the host galaxy becomes: larger, heavier in its dark matter halo, richer in its stellar halo, the accumulated residue of every smaller galaxy it has ever claimed, one that swings from very far out to very close in on each passage, experiences strong tidal forces only briefly at its closest approach, and then retreats to a distant epicenter where the tidal forces are weak and the satellite can partially recover its shape before the next approach. A satellite on a tighter, more circular orbit feels more continuous tidal stress, but never the extreme peaks of the highly elliptical case. A satellite dense with dark matter in its center, the dark matter concentrated in a compact core rather than spread through an extended halo, resists disruption more effectively because the strong central gravitational field holds the innermost material against the host's tidal pull, even as the outer regions are stripped away. All of these factors combine to produce a wide range of disruption timescales, from a few 100 million years for a low-mass satellite on a tight orbit to several billion years or more for a massive dense satellite on a wide and slowly decaying path. Some of the dwarf galaxies visible in orbit around the Milky Way today are only beginning this process. They retain their shapes, they hold their stars in coherent bound systems. They have not yet made enough pericenter passages to have lost significant fractions of their mass, or they are massive enough that even many passages have left their cores intact. Others are deep into the process, their outer regions long since surrendered, their cores still orbiting but diminished, leaving behind them streams of stars that arc across large fractions of the sky, the visible remnants of everything that has already been lost. And some have been absorbed so completely that nothing recognizable remains of the original structure, only a population of stars now distributed through the Milky Way's stellar halo, still carrying in their chemistry and their orbital motions the faint but readable signature of the galaxy in which they formed, billions of years ago, before that galaxy ceased to exist as a separate object. The Milky Way's stellar halo is not smooth. It is not a featureless glow of old stars, diffused evenly through the volume of space surrounding the galaxy's disk. When mapped with sufficient precision, when the positions and motions of enough individual halo stars are measured carefully enough to reveal structure at the scale of individual streams, it resolves into a complex, layered architecture of ribbons and arcs and coherent moving groups, each one the remnant of a galaxy that has already been consumed. Some of these streams are broad and old, their stars dispersed across wide swaths of sky by billions of years of orbital precession and the gravitational perturbations of the Milky Way's disk and bulge. Others are narrow and relatively young, their stars still tightly clustered along the orbital path of the galaxy that produced them, not yet dispersed enough to lose their shape. Each one represents a chapter in the Milky Way's history of growth, a moment when a smaller galaxy was drawn close enough, held long enough, and stripped thoroughly enough to contribute its stars to the larger structure. The stars in those streams are old. Most of them formed in the early universe, when the dwarf galaxies that produced them were themselves young and star-forming, before the Milky Way's gravity had yet interrupted their independent lives. They burned through generations of stellar evolution in their birth galaxies, the most massive among them ending as supernovae that enriched the gas of those small galaxies with heavy elements forged in their cores, the less massive ones surviving to the present as faint, ancient, low-mass stars that have been burning quietly for 10 billion years or more. When the tidal forces of the Milky Way finally pulled them free of their birth galaxies, nothing about their internal physics changed. They continued to burn, they continued to age, they carried with them the chemical record of their birth environment, the specific mix of elements their birth galaxy's star formation history had produced, and that record persists in their spectra today, readable by instruments sensitive enough to resolve the fine structure of stellar absorption lines, distinguishable from the stars that formed inside the Milky Way itself, if the measurements are precise enough and the sample is large enough. A stellar stream, then, is two things at once. It is a collection of stars currently distributed along an arc of sky, moving in coherent patterns that reveal their common origin and their shared orbital history. And it is a chemical archive, a sample of material from a galaxy that no longer exists, carrying in the abundance ratios of its constituent stars, the record of how star formation proceeded in that galaxy before the Milky Way's gravity intervened. The stream is both the shape of a past orbit and the chemistry of a past world. Both kinds of information are present simultaneously, encoded in the same stars, readable by the same instruments if those instruments are turned toward the right patch of sky with sufficient patience and precision. This dual nature of stellar streams, kinematic fossil and chemical archive together, is what makes the Milky Way's stellar halo so rich as a record of the past. A smooth, featureless halo would tell very little. A halo that consisted only of smoothly mixed accreted material, dispersed over billions of years into a uniform background, would preserve no information about the individual galaxies that had contributed to it. But the halo is not smooth. It is structured, layered, full of coherent moving groups and chemical populations that trace back to distinct progenitor galaxies, some of them already well characterized, and others still waiting to be identified and mapped. Each stream discovered adds a page to the record. Each chemical population separated and analyzed adds detail to the picture of what the Milky Way was built from, and when, and how many smaller galaxies contributed to its present form. The largest of those consumed galaxies would have been substantial, not small dwarf galaxies with a few million stars, but objects with masses of hundreds of millions, or even billions of solar masses, galaxies that might have been visible from across the local group, whose contribution to the Milky Way's structure was not just a thin stream in the stellar halo, but a deep reorganization of the inner galaxy, a stirring of the existing stellar populations, a merging of kinematic and chemical histories that shaped the thick disk and the inner halo and the structure of the bulge. These ancient major mergers are harder to read than the streams left by smaller, more recent infall events, because the greater violence of the merger process and the greater time elapsed since it occurred have had more opportunity to disperse and mix the accreted material. But the signatures are still there, not in ribbons of stars on the sky, but in the statistical properties of large stellar populations, in the characteristic shapes of the orbits that halo stars follow, in the chemical abundance patterns that distinguish one accreted population from another, even when all spatial coherence has been lost. The small, recently absorbed galaxies leave ribbons. The ancient, massive mergers leave subtler marks. Between the two extremes lies the full history of the Milky Way's growth, preserved in the stellar halo in layers of information at different levels of accessibility, waiting for the right surveys and the right analytical tools to render it legible. Some of that history is already being read. Some of it will be read in the coming decades as new observational programs accumulate the data needed. Some of it may remain beyond reach, erased by time and dynamical mixing, beyond the possibility of reconstruction. The record is rich, but it is not unlimited. And what is already visible, the streams, the chemical populations, the coherent moving groups of halo stars tracing the orbital paths of galaxies consumed long ago, is remarkable enough on its own terms, without needing the promise of what may yet be found. Consider the geometry of a stellar stream as it would appear to an observer positioned somewhere above the Milky Way's disk, looking down at the full expanse of the galaxy and its surrounding halo. The disk itself is a flat spiral structure, its bright arms and dense center familiar from every image of a galaxy like this one, around the disk extending far above and below, and to all sides, the halo, diffuse, faintly glowing with old stars, largely invisible in ordinary light. And threaded through that halo, winding in great arcs that follow inclined planes, cutting across the disk at various angles, the streams, thin bright curves of stars, each one following the ghost of an orbit, leading tail ahead and trailing tail behind. The arcs of different streams crossing and overlapping, and at different distances from the galaxy's center, some close in and some reaching far out into the outer halo, together composing a three-dimensional web of orbital history that extends hundreds of thousands of light years in every direction. From inside the Milky Way, this structure projects onto the sky in ways that are harder to untangle. The streams appear as arcs and bands of stars crossing the sky at various angles. Their three-dimensional geometry collapsed into 2 dimensions by the perspective of an observer embedded within the system, separating them from the background of Milky Way stars, identifying which stars belong to which stream, measuring the distances and velocities needed to reconstruct the three-dimensional path of each stream. All of this requires surveys of sufficient depth and precision that only the most recent generation of astronomical instrumentation has made possible. The streams were there all along. The stars that compose them were visible in the sky, but without the ability to measure the precise distance and velocity of each individual star, to separate the small systematic signal of a coherent moving group from the vast background of unrelated field stars, the streams were invisible inside the noise. They became visible only when the data became detailed enough to reveal them. Each stream that has been identified represents a galaxy that is gone, not destroyed. Its stars still shine, still burn, still age, but dissolved as an independent structure, its stars no longer held together by a common gravitational center, no longer moving together as a bound group, but drifting slowly apart along the shared arc of their former orbit. The galaxy that made those stars no longer exists in any form that would be recognizable to someone who knew it before the Milky Way's gravity began its work. What persists is only the record, the spatial distribution, and the orbital motions of the stars, the chemical abundances preserved in each star's spectrum, together constituting something more like an echo than a remnant, a shape in the pattern of stellar positions, a tendency in the distribution of stellar velocities, a signature in the ratios of element abundances that no time or mixing can erase so long as the individual stars survive. And many of those stars will survive for an enormous time to come. The faintest, least massive among them, the ones that burn their fuel most slowly, that have been shining since the early universe, and will continue shining for longer than the current age of the universe again, will persist long after the galaxy that created them has been thoroughly absorbed, and the stream that marked its dissolution has itself been mixed beyond recognition into the general stellar halo. They will carry their chemical records intact into a future so distant that the Milky Way itself will have changed beyond recognition, transformed by its own ongoing history of growth and merger and evolution. In that far future, someone with instruments sophisticated enough to read a stellar spectrum and interpret its elemental ratios might still be able to identify a handful of ancient stars and trace them back through the logic of stellar chemistry and orbital dynamics to a small galaxy that was absorbed long before the present moment. The record that persistent and that deep and that quiet. A stellar stream is what remains when a galaxy is consumed and its identity dissolved into the larger whole. It is not a dramatic remnant, not a bright explosion, not a cloud of heated gas, not a visible scar on the face of the absorbing galaxy. It is a ribbon of stars moving in slow concert along the path of a vanished orbit, their light faint, their distribution sparse, their coherence preserved only in the precision of their positions and velocities. It carries the geometry of a former orbit. It carries the chemistry of a world that no longer exists as a separate place in the universe. And it persists, slowly dispersing across astronomical time, gradually losing its coherence to the differential precession of orbits in the complex gravitational landscape of the host galaxy, but still readable for hundreds of millions of years after the galaxy that produced it has been thoroughly absorbed. There is something in the nature of that persistence worth dwelling on. The galaxy is gone, the stars remain, the record remains. The tidal forces that pulled the galaxy apart did not destroy anything at the level of the individual star. Each sun that was stripped from its birth galaxy continued to burn through the same nuclear processes, continued to fuse hydrogen in its core or helium in its shell, depending on its age, continued to age at the rate its mass dictated. The disruption was a reorganization, not an annihilation. What was a bound group became an unbound arc. What was a separate gravitational system became a contribution to a larger one. The stars moved from one context to another, from membership in one galaxy to membership in another, without any of them experiencing anything that would register as an event at the scale of the star itself. Vast by any human measure, quiet at the scale on which it operates. The dark is very old in the space between these stars. It has been dark there for longer than the Earth has existed, longer in many cases than the sun has been burning. The stars in a stellar stream are spread so widely that the distance from one to the next is typically several light years, meaning that each star sits in its own pool of darkness, surrounded by the void, its nearest neighbor so far away that the light passing between them takes years to arrive. The stream as a whole spans thousands of light years. Its individual stars are solitary points of light in an enormous darkness, and yet they are connected, not by any physical medium, not by any force other than the shared geometry of their common history. The fact that they were once part of the same small galaxy and were stripped from it together long ago and have been following the same great arc through the Milky Way's halo ever since, drifting slowly apart, the stream widening with each passing million years as the stars at slightly different energies slowly diverge. In a billion years, in several billion years, the stream will be too dispersed to identify as a coherent structure. The stars will have spread along their arc until the density contrast against the background halo is too small to measure. The orbital history will no longer be readable in the spatial distribution of the stars, though it may still be readable, faintly, in the statistical clustering of their velocities and orbital energies, and the chemical record will persist still longer, locked in the spectra of the individual stars themselves, carried forward into the deep future, waiting. The galaxy that left this record behind has been gone for a long time. The record it left behind will outlast the capacity to read it by a margin that no unit of human time can conveniently describe. What the record shows, while it remains legible, is not a catastrophe. It is a transfer, mass moving from a smaller structure to a larger one, the smaller structure ceasing to be a separate thing and becoming part of the larger thing, the whole process unfolding over timescales so vast that nothing within either galaxy experienced it as an event. The stars that were stripped continued to shine. The stars that remained in the core of the dwarf galaxy continued to orbit it. The stars that were already part of the Milky Way continued on their own orbits, largely unmoved by the addition of new members to the halo. Gravity did its slow and patient work, and when it was done, when the dwarf galaxy's outer regions had been fully surrendered and only a depleted core remained, still orbiting, still slowly giving more of itself with each closed passage. What remained visible in the sky was a ribbon of stars following a great arc, faint and quiet and full of information, the preserved signature of a galaxy that had become part of something larger. That ribbon persists long after the galaxy that made it is gone. It drifts through the Milky Way's halo in the slow dark, its stars still burning, its arc still tracing the memory of a former orbit, its chemistry still carrying the record of a star formation history that played out in a small and distant galaxy billions of years ago. It is a remnant of consumption and also a form of continuity, the past written in light, still legible, still present in the sky above any world patient enough to look for it. In the autumn of 1994, in a building at the University of Cambridge, a young astronomer named Rodrigo Ibata was sorting through spectra taken from a telescope in the mountains of Chile. The spectra were measurements of individual stars in the direction of the Milky Way's central bulge, the dense, ancient, swelling heart of the galaxy, where stars crowd so thickly that observing anything through or beyond them is something like trying to read a sentence through a jar of clouded honey. What Ibata was looking for was motion. Each spectrum, if read carefully, would reveal how fast a star was moving toward or away from Earth, a velocity encoded in the slight compression or stretching of the light the star emits. And in the data, something was wrong. A group of stars did not belong. They moved together, sharing nearly the same velocity, and that velocity did not match the velocity of the Milky Way stars surrounding them. Stars in the Milky Way's bulge do not move as a collective. They orbit on their own individual paths, spread across a range of speeds. These stars were different. They were coherent. They were traveling together through space at the same pace, as if they had come from somewhere else, as if they had once been part of a single object that was no longer visible as an object, and yet was still present, dispersed through the line of sight behind all those Milky Way stars, disguised as belonging to a crowd. It had only recently joined. Ibata and his colleagues Gerard Gilmore and Michael Irwin recognized what they were seeing. Hidden behind the Milky Way's central bulge, at a distance of roughly 26,000 light-years from the galactic center, was a galaxy. Another galaxy, entire, sitting inside the Milky Way's own body, without anyone having noticed for the whole long history of telescopic astronomy. It was called the Sagittarius Dwarf, spheroidal galaxy. The name was given to the small, dense region of stars where the original detection was made, the surviving core of a system that was, at the time of the announcement, still intact enough to be called a galaxy by any reasonable measure. It was compact. It was old. Its stars were mostly ancient, formed in the early universe, metal poor in the way of things that assembled before many generations of stars had lived and died and scattered heavier elements into the clouds their successors would be born from. By the standards of a dwarf galaxy, it was not extraordinary. It had a mass in stars of perhaps 1 billion solar masses at its peak, and a far larger dark matter halo wrapped around it. But it was close, so close that it had already been in contact with the Milky Way's gravitational field for billions of years, and the contact had left marks. The stars in the surviving core are held together more loosely than they would be in an undisturbed galaxy. The core itself is elongated, its shape pulled and stretched along the axis pointing toward the galactic center. Around it, in all directions, the outer stars of the Sagittarius Dwarf have already been stripped away, not violently, not quickly, but one orbital passage at a time, each close approach peeling another thin layer from the outermost reaches of the galaxy and depositing those stars into the Milky Way's own halo. The process has been running for billions of years. The galaxy that Abada and his colleagues found in 1994 was already, at the moment of discovery, mostly gone. What remained was a dense remnant, a nucleus, still glowing, but surrounded on all sides by the stars it had already surrendered. The surrendered stars do not vanish. That is the essential quality of this slow dissolution. It is not destruction in any ordinary sense. The stars torn from the Sagittarius Dwarf continue to shine exactly as they did when they belonged to their birth galaxy. They do not die or dim when they cross the boundary into the Milky Way's halo. They simply travel on, following the orbital path that was once their galaxy's path, strung out along that trajectory like beads slipping from a thread, some of them running ahead of where the remnant core now sits, some of them trailing far behind. Over enough time, those two streams of stars, the ones running ahead and the ones falling behind, extend across enormous fractions of the sky until a telescope that can identify them by their chemical signatures or their orbital properties finds them not in one region of the sky but everywhere. The first comprehensive mapping of those two streams came in the early years of the 21st century, using data from a survey that had spent years photographing the sky with a dedicated telescope in the mountains of New Mexico. When the survey's stellar maps were searched for concentrations of stars sharing the colors and brightnesses expected of old metal-poor stars at particular distances, a pattern emerged that was unlike anything the survey had been built to find. The stars formed a great arc, not a ring, not a patch, not a smudge, an arc, a continuous curving structure of stars, wrapping more than 200 degrees around the sky. It was a stream in the astronomical sense, a ribbon of stars winding through the Milky Way's halo, ordered by gravity, coherent in direction, traceable from one end to the other, across distances ranging from roughly 13,000 to more than 100,000 light-years from Earth. 200 degrees of sky is a large fraction of everything visible. It is more than a hemisphere. Across that span, the Sagittarius stream, as the structure became known, contains stars at different distances, different depths, different stages of separation from their source. The closest parts of the stream are stars that were stripped relatively recently, still not far from the surviving remnant in orbital terms. The most distant parts are stars released billions of years ago, stars that have been traveling along the same orbital path so long that they have lapped the galaxy, arrived at a position on the sky far from the remnant, and continued on. When astronomers looked closely at the distances involved, they found not one simple ribbon, but a multi-wrapped structure, two distinct loops detectable at different ranges, one closer to Earth, one farther, the geometry of repeated orbital passages written out in faint starlight. What this means physically is that the Sagittarius Dwarf has passed through or close to the Milky Way's central region more than once. Each passage was a kind of tidal stripping event, the orbital equivalent of dipping a soft stone into a current and pulling it out slightly smaller each time. On the first passage, the outermost stars were stripped. On the second passage, the next layer was stripped, and those stars joined the stream at a different position and a different distance because the orbital parameters had shifted slightly after the first disruption. The geometry of the two-loop stream is a record of those passages, a timestamp in the orbital structure, a way of reading the history of the disruption from the positions and distances of the stars themselves. No instrument observed those passages. They happened billions of years before there were instruments to observe anything, but the stars remember where they were and how fast they were moving, and that memory is precise enough to read. Among all the material released from the Sagittarius Dwarf across all its orbital passages, the total mass of stars now distributed through the Milky Way's outer halo is very large. In some regions of the sky, particularly in the outer halo, where the native Milky Way star density is low, a quarter or more of all the stars present may originally have formed inside the Sagittarius Dwarf. They are not recognizable by eye or by position alone. They sit mixed among the rest of the halo, indistinguishable in appearance from any other old star at that distance. But they are distinguishable by chemistry. Stars carry the chemical record of the gas clouds they were born from. The proportions of different elements in a star's atmosphere, captured at the moment of formation and largely preserved for billions of years, reflect the history of nucleosynthesis that had already occurred in the star's birth environment. In particular, the ratio of what are called alpha elements, such as magnesium and calcium, to iron carries information about how rapidly the galaxy that produced the star had been forming stars at different epochs. A galaxy that formed stars quickly and then slowed will have a different chemical signature in its oldest stars than a galaxy that formed stars slowly and steadily. The Milky Way's disk and bulge formed stars very intensely in their early history, seeding the interstellar medium heavily with alpha elements before iron from longer-lived supernovae could catch up. The Sagittarius Dwarf, smaller and slower in its star formation, accumulated iron from those longer-lived stellar deaths more gradually, producing stars with a lower alpha to iron ratio at intermediate metallicities. That difference is small. It is not something visible in any ordinary sense. It is a measurement, precise spectroscopy, individual absorption lines, compared against theoretical models, a slight but consistent and measurable shift in the proportions of elements, forged by different categories of exploding stars. In the spectrum of a single old halo star, the shift is subtle. Across a sample of thousands of halo stars with measured chemical abundances, the shift becomes a population, a distinct cloud of points in the multidimensional space of stellar chemistry. Sitting in a region of that space that the Milky Way's native stars do not occupy, each one of those chemically distinct halo stars is an emigrant. It formed inside the Sagittarius Dwarf, lived there for some portion of its billions of years' life, and was deposited into the Milky Way's halo when the orbital passage came close enough to strip it away. Now it spends its remaining billions of years of stellar life as a Milky Way star, orbiting the same galactic center as every other halo star, chemically marked but gravitationally integrated. The surviving core of the Sagittarius Dwarf today contains somewhere between 20 and 50 million solar masses of stars, against the original estimated total mass of the system, including its dark matter halo, which may have been anywhere from 10 billion to 100 billion solar masses before infall. That is a very small remainder. The vast majority of the original Sagittarius system has already been deposited into the Milky Way's halo, or absorbed into its diffuse dark matter distribution. What remains is not a normal galaxy. It is a remnant, coherent enough to be called a structure, with a stellar density higher than the surrounding halo, and a position on the sky distinct enough to study, but already so disrupted that it will not remain recognizable as a separate object indefinitely. The stripping continues. Each orbital passage removes more. The remnant is smaller than it was when Abada found it, and it is smaller today than it will be after the next close approach. At the center of the remnant, something has survived that the surrounding dissolution has not reached. It is a globular cluster, a dense spherical grouping of hundreds of thousands of old stars, bound to each other by their own gravity, ancient in the way that almost nothing else is ancient. It is called M54, and it sits exactly at the core of the Sagittarius remnant, at the gravitational center of what remains of the galaxy that brought it here. Globular clusters are common in galaxies. The Milky Way has more than 100 of them. Most formed early in a galaxy's history and have orbited their host ever since, slowly spreading their stars through internal dynamical processes, but remaining gravitationally bound for billions of years. Many of the globular clusters now associated with the Milky Way may have arrived with accreted dwarf galaxies, imported along with the stars and dark matter of the satellites the Milky Way consumed. MIM54 is different from those. Its position at the precise center of the Sagittarius remnant, its velocity matching the remnant exactly, and its extreme mass, it is one of the most massive globular clusters associated with the entire Milky Way system, have led to the understanding that M54 is not an ordinary globular cluster that happened to orbit the Sagittarius Dwarf in a central position. It is the nucleus of the Sagittarius Dwarf. It is what remained when the galaxy's original central stellar concentration collapsed and densified over billions of years, gathering the densest and oldest stars at the gravitational core of the system. What appears in a telescope image as a tight, brilliant sphere of ancient light is the preserved heart of a galaxy. Around it, in every direction, the galaxy's outer body has already dissolved into the Milky Way. Its dark matter is gone, merged with the Milky Way's own dark matter halo. Its outermost stars are in the stream, distributed across 200 degrees of sky. Its intermediate stars are in the halo, orbiting the galactic center on their own slow paths, their origin recorded only in the subtle chemistry of their atmospheres. What remains is the nucleus, still dense, still luminous, still orbiting at the center of whatever is left of the system it once anchored. This picture, a galaxy consumed nearly entirely, its nucleus still intact, at the center of a dissolving remnant, its stripped stars wrapped in two great loops around the sky, did not arrive all at once. It accumulated over decades, built from spectroscopic surveys and photometric catalogs, and the enormous effort of comparing the properties of millions of individual stars to the predictions of theoretical models. The stream itself was not obvious in any single image. Its surface brightness, the amount of light it contributes per area of sky, is far too low to see with the eye, or even in a single photographic exposure. It is found statistically by asking whether the number of stars of a particular type in a particular part of the sky is slightly higher than the number that would be there if the halo were smooth, and in the direction of the stream, it is. Not enormously, not obviously, but measurably, consistently, repeatably, and the stars that constitute the excess share the chemical properties expected of Sagittarius origin stars, which closes the argument. The stream is real. Its geometry is the geometry of a galaxy coming apart across billions of years of repeated gravitational interaction with a much more massive neighbor, running alongside the stream at a different depth in the halo, Older portions of the stripped material drift in orbits that have already diverged enough from the stream's current path that they no longer form a tight ribbon. They spread, slowly, into a broader, more diffuse population of halo stars. Given enough time, given a few more billion years of orbital evolution, even the stream will spread and diffuse, its coherence lost to the slow gravitational churning of the galaxy, its stars indistinguishable in position from all the other ancient halo stars surrounding them. The chemistry will remain. The chemical signature of Sagittarius origin will persist in the individual stars for as long as those stars shine. But the ribbon structure, the legible arc of starlight tracing the original orbit, will fade. The record will become harder to read, and the galaxy from which it came will be, in any meaningful sense, gone. The remnant core will also dissolve eventually. The stripping that has already reduced the Sagittarius Dwarf from a 10 billion solar mass system to a remnant of tens of millions of solar masses will continue until the remnant is too small and too disrupted to maintain even the loose coherence it has now. What that endpoint looks like is not fully certain. It may be that M54 survives as a dense cluster orbiting the Milky Way long after the last recognizable trace of the galaxy surrounding it has been absorbed. Globular clusters can survive enormous spans of time. They are gravitationally robust objects, their internal stellar density high enough to resist the tidal forces that have already stripped everything around them. If M54 is the nucleus of the Sagittarius Dwarf, and if it survives, then the Milky Way will eventually have incorporated a new globular cluster carrying no visible sign of the galaxy it once anchored, only its ancient stars, still orbiting, still shining, their chemistry still marked with the signature of a different birth environment. There is a quietness to this outcome that is easy to miss when describing the forces involved. The tidal forces are not quiet in any intuitive sense. The differential gravitational pull across the body of a dwarf galaxy, stronger on the near side, weaker on the far side, is the expression of a gravitational field of hundreds of billions of solar masses. But because these forces act over timescales of billions of years, their effect is not a sudden tearing, but a slow, steady, patient erosion, the way a river does not strike stone, but simply persists against it until the stone is somewhere else. The stars that left the Sagittarius Dwarf in its first orbital passages billions of years ago did not know they had left. There was no moment of departure. One orbital period, they were loosely bound to their birth galaxy, and over the next they were no longer bound at all, and they continued on their orbits through the growing space of the Milky Way's halo, uninterrupted, unchanged, carrying only the chemical memory of where they came from. The Sagittarius Dwarf is often described in terms of its eventual fate: consumed, absorbed, dissolved, and all of those descriptions are accurate, but they emphasize an ending over the long, ongoing, still incomplete process that continues right now. The core still orbits, the stream still stretches, stars are still being stripped from the remnant on each pericenter passage, still being added to the halo, still carrying their chemical signatures into the vast and mostly empty space of the outer galaxy. From a perspective that can hold the full timescale, the Sagittarius Dwarf is not a finished story. It is a story in the middle of its longest chapter, a galaxy that has been losing itself for billions of years, that has lost most of what it was, and that continues with extraordinary patience to lose the rest. The stream it has left behind, those two great loops of chemically distinctive stars, arcing across more than 200 degrees of sky, is the most complete record available of a galaxy in the process of being consumed. Every other galaxy the Milky Way has absorbed in its long history of accretion has left a record too, but most of those records are older, more diffuse, more thoroughly mixed into the halo. The Sagittarius stream is fresh enough, by galactic standards, that its structure is still readable, its two loops still geometrically coherent, its chemistry still sufficiently concentrated in particular sky regions to be mapped. In this sense, it is a gift to the study of galactic cannibalism, not because of what it reveals about destruction, but because of what it reveals about preservation. A galaxy can be almost entirely consumed, reduced to a fraction of its original mass, its dark matter already merged into the host, its outer stars already distributed through 100,000 light-years of halo, and the process still leaves behind enough coherent, legible evidence to reconstruct the orbital history, the chemical history, the mass history of what was lost. The stars in the stream are ancient. Many of them are older than 10 billion years, older than the current configuration of the solar system, older than the planets, older than Earth, by more than 5 billion years. They were already old when the first complex organisms appeared in Earth's oceans. They were already old when the continents reached something close to their current shapes. In the billions of years they have spent as stripped stream stars rather than members of their birth galaxy, the entirety of visible complex life on Earth rose and diversified, and in some lineages ended, and in others continued. Those stars traveled none of that. They simply orbited,
moving through the outer halo at velocities of a few hundred kilometers per second, completing their long elliptical paths around the galactic center, once every several 100 million years, carrying their chemical memories through a space so empty that the nearest other star at any given point in the stream is still several light years away. There is nothing urgent about any of it. There is nothing tending toward a conclusion on any timescale that includes a human life, or a civilization, or even a species.
The remnant of the Sagittarius Dwarf will continue to dissolve across the next several 100 million years. MIM 54 will continue to orbit at the center of that dissolving remnant, growing gradually more isolated as the surrounding stars disperse, until it is only a globular cluster, still dense, imbued its nature as the nucleus of a consumed galaxy, visible only to someone who knows what chemistry to look for and what orbital statistics to compare. The stream stars will continue to spread, losing their ribbon-like coherence over billions of years, becoming eventually just a slight excess of chemically distinctive halo stars in certain orbital families, readable in large survey datasets, but no longer traceable as a structure. And M54 itself will sit there, dense and old and luminous, the way that globular clusters are luminous, not with the bright active light of a galaxy still forming stars, but with the steady ancient glow of 100,000 old stars that have been burning hydrogen since before the solar system existed, that will continue burning long after the sun has exhausted its fuel and cooled. When the last recognizable trace of the stream has been mixed into the halo, and when the last recognizable trace of the remnant has been absorbed into the Milky Way's general stellar population, M54 will remain, not as a galaxy, not as a nucleus, simply as a cluster, one of more than 100 clusters in the Milky Way's system, each with its own history, each a different kind of survivor, orbiting slowly on the long elliptical path it has followed for billions of years, the stars inside it shining as they have always shone, without record of what surrounded them once, without memory of the galaxy they anchored, without knowledge of any of it. Only the light remains, and the light, patient and cold and ancient, continues outward through the halo in every direction, as it always has, reaching the Milky Way's outer reaches and continuing into the void beyond, carrying nothing but itself. A few hundred stars hang in a region of space roughly 29 light years across. Not a cluster, not a cloud, not a bright arm of something larger, just a scattering, faint, old, and spread so thinly across that volume of sky that even a deep telescope image shows them as individual points, each one resolvable, each one countable. There are so few of them that astronomers have in fact counted them. The total light they produce together is less than the light of a single moderately bright star visible to the naked eye on a clear night. A single star outshines an entire galaxy, and yet this faint scattering is a galaxy. It has a name. It has a measured depth and width. It contains a dark matter halo, hundreds of times more massive than its own starlight could suggest. And that dark matter halo is what makes it, unmistakably, a galaxy rather than a loose association of stars drifting apart. The object is called Sagittarius 1, and it is among the smallest, faintest, most dark matter-dominated galaxies known to exist anywhere in the observable universe. The stars inside it are old. Their light carries the chemical record of an early universe, when the raw material of stars was still mostly hydrogen and helium, when the heavier elements had not yet been built and scattered by enough generations of stellar death to leave a strong trace in anything newly forming. These stars are metal poor, in the language astronomers use, not poor in the metals of hardware stores and cooking pans, but poor in the elements forged in stellar cores, which to an astronomer means almost everything heavier than helium. They are ancient. They formed when the universe was young and have been burning slowly ever since, suspended in a structure so diffuse it is almost invisible, embedded in a halo of dark matter that holds them together across a span of decades of light travel time. To stand at the edge of Sagittarius 1 and look inward would be to see almost nothing. The nearest neighbor star might lie several light years away. The sky would be a strange, near empty field with a few dozen stars visible at modest distances, each one isolated and dim against the larger background of the universe. The Milky Way itself would glow on one side, a great diffuse band of light, already noticeably close, its gravity already noticeable, already pulling at the outermost stars of this small, quiet, nearly invisible world. The stars of Sagittarius 1 do not move quickly relative to one another. They drift at a few kilometers per second in orbits around the shared gravitational center of the system. That sounds slow, and for a gas of ordinary objects, it would imply a very low mass. But when astronomers measure those velocities with spectroscopes, reading the slight shift in each star's light caused by its motion toward or away from the telescope, and then calculate what mass is needed to keep those stars gravitationally bound, the answer comes back much larger than the stars themselves can account for. The visible matter is not enough, not nearly enough. The stars are held together by something that produces no light, and the mass of that something outweighs the mass of the stars by more than a factor of 1,000. The ratio of total mass to light-producing mass, the mass-to-light ratio, exceeds 1,000 in solar units. In ordinary galaxies, including the Milky Way, that ratio is much lower. In Sagittarius 1, the visible stars are almost irrelevant to the gravitational accounting. They are tracers. They are the detectable surface of something mostly invisible. The dark matter halo surrounding those few hundred stars is not dramatically different in its physical nature from the dark matter halos surrounding much larger galaxies. It is simply smaller. It has the same basic properties, distributed in a roughly spherical arrangement, denser at the center and thinning gradually outward, responding to gravity but not to light or to the electromagnetic force. It cannot be seen directly. Its presence is inferred entirely from the behavior of the stars that move within it, The way the depth of an ocean can be inferred from the behavior of waves on the surface, even when the bottom is invisible. The stars are the surface. The dark matter is the depth. To understand why this matters, why a few hundred ancient stars in a sparse cloud constitute a galaxy rather than a cluster, it helps to feel the difference in scale between what can be seen and what is actually there. Imagine holding up a small glass bead, 2 or 3 millimeters across. Somewhere you can see the whole room around it. The bead is the visible starlight of Segway. The dark matter halo extends to a distance that, on the same scale, might fill a house. The bead is real. The house is real. The house is the galaxy. The bead is just the part that can be photographed. Willman 1 is another object of this kind, discovered around the same time as Segway 1, in the middle years of the first decade of this century. When a major photometric survey of the sky was producing data detailed enough to find objects that had never been detectable before, it appeared initially as a slight overdensity of faint stars in one patch of sky, a statistical excess. More stars in one place than the smooth background distribution would predict, at distances consistent with one another, colors and brightnesses consistent with an old metal-poor stellar population. The signature not of a visible structure, but of a concealed one, detectable only through careful comparison of what was observed against what a blank sky should look like. At first, the nature of Willman 1 was not certain. A galaxy and a globular cluster, a self-gravitating sphere of stars born together from one cloud of gas, can look superficially alike at great distances, if the cluster is old and its stars have the right colors. The question that separates them is whether dark matter is present. Globular clusters have little or no dark matter. They are gravitationally bound by the mass of their own stars, and their internal velocities match what those stars alone could produce. Galaxies, even the smallest and faintest, have dark matter halos that dominate the gravitational accounting. When spectroscopic measurements of Willman 1's stellar velocities came in, the stars were moving too fast to be held by their own mass alone. Something else was there. Something unseen but gravitationally real. Willman 1 was a galaxy. It also showed signs of being pulled apart. The distribution of its stars was not quite symmetric. One side appeared slightly extended, slightly stretched, in a direction that pointed loosely toward the center of the Milky Way. This elongation, mild, uncertain, but detectable, suggested that the Milky Way's tidal forces were already at work. The outer stars were being nudged, gently and steadily, toward the larger galaxy's gravitational center. Not dramatically, not all at once, the way a candle flame leans in a very slow draft. The drift is almost imperceptible, but it is there, and over long time it adds up to something. This is what tidal disruption looks like at the scale of the very small. Not a dramatic tearing, not a visible catastrophe, just a slight asymmetry in the distribution of stars, a gentle elongation along the axis that points toward the greater gravity, the outermost members of the system beginning to loosen from it one by one. The stars that leave do not vanish. They continue in orbits shaped by the encounter, spreading slowly along the path the galaxy traced on its way past, forming the faint beginnings of a stream that may eventually wrap around the sky. For objects as faint as Segway 1 or Willman 1, finding that stream is not yet possible. The signal is too faint, the stars are too sparse, too individually dim, too hard to distinguish from the background population of the Milky Way's own halo. But the physics does not require that the stream be visible to be real. If the disruption is happening, and the velocities and the elongations suggest it is, Then somewhere behind these galaxies on their orbits, a thin trail of stars is already accumulating, a signature too faint for current instruments, but waiting in the sky to be read when better ones arrive. The discovery of these objects, Segue 1, Willman 1, and the growing number of similar systems found across a little over 2 decades of sky surveys required a specific technique. It is called a matched filter search, and it works by looking not for a visible patch of light, but for a statistical pattern in a catalog of stars. Every star in a deep photometric survey is characterized by its apparent brightness and its color, two quantities that, combined, place it somewhere in a diagram of stellar types. An old metal-poor stellar population at a specific distance will produce stars that fall in predictable locations in that diagram. They will have particular colors, particular apparent magnitudes. To search for an ultra-faint dwarf galaxy is to ask, across the entire sky, cataloged by a survey, is there any region where the stars that would belong to a population like this are slightly more numerous than the smooth background predicts? Is there a patch, perhaps a few tenths of a degree across, where the counts are anomalously high for stars with the right colors and the right apparent magnitudes to be old, metal poor, and nearby, the search is purely statistical. No glow is expected, no visible structure, only a number that is slightly larger than it should be, in a region of sky that looks by eye like any other. When such an excess is found, it is flagged. When follow-up observations confirm that the stars in the flagged region share a common distance, a common age, a common chemistry, and velocities that require more mass than the stars themselves provide, the flag becomes a galaxy. This technique, applied to the Sloan Digital Sky Survey, a photographic atlas of a large fraction of the sky in multiple color bands, built up through observations during the first years of this century, more than doubled the known satellite galaxy population of the Milky Way within a few years of the survey's data becoming available. Before the survey, only a handful of dwarf satellite galaxies were known, the bright and obvious ones visible through small telescopes in the southern and northern skies. The survey revealed that the population extended far downward in luminosity into a regime where the word galaxy no longer matched the intuitive picture of a glowing swirl of stars, but still matched the physical definition, a self-gravitating system dominated by dark matter, containing a stellar population with a coherent history, bound to the Milky Way as a satellite. The count grew. A dozen known satellites became 24, then more. Objects with names reflecting their discovery circumstances, the name of the constellation in which they appeared, or a number, or the name of the survey that found them, accumulated in the literature, each one a faint world, each one a dark matter-dominated structure, too small to have gathered enough gas to form many stars, too small to have held on to the gas it did gather against the heating and pressure of the early universe, its star formation quenched early and completely, leaving behind only the ancient stellar record of a brief limited epoch of formation. The question of why there are so few stars, why the dark matter halo is so massive relative to the stars inside it, reaches back to the era just after the first stars and galaxies formed, when the universe was flooded with ultraviolet light, energetic enough to ionize hydrogen gas throughout the intergalactic medium. This era, called reionization, suppressed the ability of small dark matter halos to gather and cool gas into stars. A halo below a certain mass threshold could not hold on to gas against that radiation pressure. Whatever gas it had would be stripped or heated away before it could collapse and form stars. Only the dark matter remained, holding together in a gravitational structure too small and too diffuse to be seen, carrying its small fraction of stars, formed perhaps just before reionization in the brief window when conditions allowed it, forward through cosmic time, invisible and patient, orbiting the Milky Way for billions of years before any instrument sensitive enough to find it existed. So these objects are in a sense relics, not of a galaxy in full operation, but of a galaxy that barely got started. The dark matter halo formed. The conditions for star formation arrived just briefly. A small number of stars formed, ancient and metal poor, from the primordial gas of an early universe that had not yet been seeded with heavy elements by many generations of stellar death. Then the window closed. The ultraviolet light of reionization swept through, or the first supernovae of those newly formed stars expelled the remaining gas, or both. The star formation stopped. The dark matter continued to orbit, carrying its handful of stars, falling eventually into the gravitational influence of a much larger galaxy, circling it for billions of years, losing a thin outer shell of stars at each closest approach, slowly contributing its sparse stellar content to the halo of the galaxy that holds it. The most extreme members of this family, the ultra-faint dwarfs, have been used as probes of a question that has no answer yet. Dark matter, whatever it is, may or may not interact with itself in ways that produce detectable radiation. One candidate for what dark matter might be, a class of particles whose nature remains hypothetical, but whose gravitational effects are well established, is predicted by some theoretical models to annihilate when two such particles meet, releasing energy in the form of gamma rays. Ultra-faint dwarf galaxies, with their extremely high ratios of dark matter to ordinary matter, are the cleanest environments in the known universe to look for this signal. There is almost no ordinary astrophysical activity in them, no star formation, no supernova remnants, no active galactic nuclei to produce background gamma ray emission that might mask or mimic an annihilation signal. They are, in this sense, quiet. The dark matter in them is concentrated and relatively undisturbed, and if any signal were to emerge from dark matter annihilation, these would be among the first places it would appear. A space-based gamma-ray telescope has surveyed these objects extensively, searching for excess emission from their interiors at energies consistent with the annihilation of various candidate dark matter particle masses. No signal has been detected. The absence of a signal is itself informative. It places limits on how strongly dark matter particles can interact with each other, ruling out some of the parameter space where a signal was expected if certain theoretical models were correct. The limits are now tight enough that some of the simplest candidate models are under real pressure. Whether those models survive, or whether the dark matter proves to be something more unusual, remains a question the data have not yet answered. The silence from the ultra-faint dwarfs is not an absence of meaning. It is a constraint. It is information written in the negative. There are now more than 60 confirmed or candidate satellite galaxies known around the Milky Way. The number was much smaller 20 years ago. It will be larger in the years ahead. A new observatory, a wide-field telescope on a Chilean mountain, designed to survey the entire visible southern sky repeatedly over many years, will produce an image archive deeper and broader than any previous sky survey. And the matched filter search applied to that archive is projected to find hundreds of additional satellite candidates. Not all of them will be confirmed as genuine galaxies. Some will be chance alignments of background stars. Some will be globular clusters. But a substantial fraction, on past experience, will prove to be dark matter-dominated systems, genuine satellite galaxies, genuine members of the Milky Way's gravitational family, some of them already disrupting, some of them still intact on wide orbits far from their closest approach. The census is not yet complete. The sky that has been searched so far covers a fraction of the full sphere around the Milky Way. The southern sky, in particular, has been less thoroughly surveyed at the depths needed to find objects as faint as Segue 1. The new observatory will change that. What it finds will fill in the map in ways that are not yet predictable, because the distribution of satellites in the sky is uneven, some clustered in certain directions, some concentrated at certain distances, the whole arrangement shaped by the geometry of past infall and the uneven distribution of the large-scale structure through which the Milky Way itself assembled. Beyond the question of how many satellites there is the question of what their population tells us about how galaxies form. Theoretical models of galaxy formation make specific predictions about the number of dark matter subhalos that should surround a galaxy like the Milky Way. For some years, those predictions were in tension with observations. The models predicted far more subhalos than observed satellites, a discrepancy significant enough to be named. The resolution of that discrepancy worked out gradually through a combination of better observations and better models involved several physical processes working together. Reionization suppressed star formation in the smallest halos, leaving them dark and undetectable. Supernova explosions in slightly larger halos expelled gas and disrupted the dark matter distribution. Tidal stripping during orbital passages around the Milky Way removed stars en masse from satellites, making them harder to find. And the observational incompleteness of earlier surveys left a large population of faint satellites simply undiscovered. As the surveys deepened and the theoretical models incorporated these processes more carefully, the tension eased, not entirely, not without remaining questions, but substantially. The ultra-faint dwarfs were a key piece of the reconciliation. The satellites that have been found, and those that are yet to be found, orbit the Milky Way at distances ranging from a few tens of thousands of light-years to several 100,000 light-years. Some are on nearly circular orbits, swinging gently around the Milky Way at roughly constant distances. Their closest approaches gentle enough that the outer stars are only loosely disturbed at each passage. Others are on highly elongated orbits, sweeping far out into the distant halo on long, slow arcs, and then plunging inward to a close approach that strips a shell of stars from their outer regions before they swing back out. The orbital shapes determine the pace of disruption. A satellite on a tight eccentric orbit loses material faster. One on a wide, nearly circular orbit can survive for a much longer time, its outer layers being gently peeled away passage by passage, the process playing out over many billions of years and many orbital periods. The stars that are stripped do not disappear. They settle into orbits around the Milky Way that closely resemble the orbit of the satellite from which they were taken, slightly ahead of it on the path, slightly behind it, forming thin tails that trace the orbital arc. Because the Milky Way's gravity is not perfectly uniform and the orbits of these stripped stars are not perfectly identical, the tails spread slowly over time, but they remain coherent for billions of years in some cases, a persistent luminous record of where the satellite was and where it was going. For the very faint satellites, those streams are themselves too faint to detect, but they are there. They accumulate in the Milky Way's halo, joining the more prominent streams left by larger, brighter satellites that have been disrupting for longer, building up the structured ribbon-threaded halo that deep surveys now begin to reveal. An ultra-faint dwarf on its first close approach to the Milky Way is not obviously different to a distant observer from one that has been orbiting for several billion years. The outer stars may be slightly extended in one direction, The surface brightness profile may be slightly asymmetric. The velocity distribution of the stars may show a small excess of stars moving in the same direction, a hint of tidal streaming, but all of these signatures are subtle, and distinguishing a slightly disrupted satellite from a completely undisturbed one requires careful measurements of many individual stars and a model of what undisturbed should look like. What is clear in all cases is that the disruption is happening. The Milky Way's gravity does not negotiate. It does not distinguish between a galaxy it has orbited for billions of years and one that has only recently crossed into its gravitational sphere. It pulls on whatever is there, with a force that depends on distance and on the mass of both objects, and it pulls the near side harder than the far side, and the difference in those two forces is what slowly, steadily, over time measured in billions of years, draws the satellite apart. And next, the process is not fast. It is not dramatic. It is the ordinary operation of gravity at cosmological scales, the patient accumulation of small asymmetric forces into a large structural transformation stretched across a span of time that dwarfs the entire history of life on Earth. It is worth sitting with that pace for a moment. The outermost stars of a satellite galaxy, being stripped by the Milky Way, are moving away from their birth system at speeds that might be measured in a few kilometers per second relative to the satellite's center. A few kilometers per second, the distance from one side of the solar system to the other, covered in a day, across the depth of an ultra-faint dwarf galaxy, tens of light years. That drift accumulates into a separation of 1 light year over the course of hundreds of millions of years. The stars are not fleeing. They are drifting, and the galaxy is not collapsing. It is dissolving, quietly and completely, on a time scale longer than the Earth has existed. The stars that drift away carry their chemistry with them. They are old, and they carry the elemental ratios of a galaxy that formed its stars early, in a short burst, from gas that had not yet been enriched by many generations of stellar death. When those stars are eventually scattered into the Milky Way's halo, they join the population of halo stars with low metallicities and low ratios of certain heavier elements to iron, a chemical signature that marks them, to careful measurement, as coming from somewhere else. They are immigrants into the halo, carrying their origin in their spectra, detectable by their chemistry long after the structure they came from has dissolved beyond recognition. The smallest galaxies dissolve most completely. A system as faint as Segway 1, if it is being disrupted, will eventually spread its few hundred stars across a large arc of the sky, each one embedded in the general halo population, indistinguishable from the other faint old halo stars by position or brightness alone, distinguishable only by the careful measurement of their orbital properties and their chemical abundances. They will become part of the background. They will join the ancient dissolved material that makes up the diffuse component of the Milky Way's outer halo, where the accumulated debris of billions of years of satellite consumption sits quietly, its individual origins largely erased by the long orbital mixing that follows disruption. The dark matter halos of the disrupted satellites do not separate cleanly from the dark matter of the Milky Way. As a satellite orbit decays and its stars disperse, its dark matter halo merges gradually into the larger halo of the host galaxy, adding to the diffuse distribution of invisible mass that surrounds the Milky Way and extends for hundreds of thousands of light years in all directions. The small halos that arrive with each consumed satellite are not individually distinguishable in the final merged distribution. They blend, their separate identities are lost, What was once a distinct gravitational structure becomes part of the background gravitational field of a larger one, and there is no way to recover from the dark matter distribution alone any record of where the component pieces came from. Only the stars carry the record forward. Only the stars, with their chemical compositions and their orbital energies, preserve the signature of their origin. The dark matter can only be weighed, the stars can be read. This is why the faintest galaxies matter to the deepest questions. They are not simply the bottom rung of the ladder of galaxy sizes, interesting as a limiting case of how small a galaxy can be. They are windows into the earliest epoch of structure formation, carrying stellar populations formed before reionization changed the conditions for star formation everywhere in the universe. They are the most sensitive probes of dark matter physics available in the local universe. Their high dark matter density and their quietness making them ideal environments to search for the subtle signatures that ordinary astrophysics cannot mimic. And they are the most vulnerable prey of the Milky Way's gravity, the objects being most thoroughly and most irreversibly consumed, their small stellar populations drawn out into the halo one by one. In the years ahead, the sky will yield more of them, fainter ones, smaller ones, objects with perhaps only a few dozen stars above the detection threshold of a given survey, their galaxy status uncertain, their dark matter content inferred from the slenderest of velocity samples. The boundary between galaxy and star cluster may prove, at these extreme faint magnitudes, to be blurrier than it seemed when only the brighter satellites were known. Objects will be found that sit in the ambiguous region between the two, their kinematics uncertain, their dark matter uncertain, their classification depending on measurements not yet made with instruments not yet built. The Vera Rubin Observatory, when its 10-year survey of the southern sky accumulates into a deep, wide, precisely calibrated image of hundreds of millions of stars, will be the instrument that makes those measurements possible, not for individual ambiguous objects, but for the population as a whole. Hundreds of new satellite candidates are expected. The matched filter search applied to a data set of that depth and breadth will return excesses so faint that current surveys cannot even approach them. Some will be confirmed. Many will require spectroscopic follow-up, measuring the velocities of individual stars in systems that may contain only a handful of stars bright enough to observe. The work will take years. The confirmations will come gradually. The map will fill in slowly, as all good maps do. What that map will show, when it is far enough along to interpret as a whole, is the full surviving population of the Milky Way's gravitational companions, the remnant of an original population that included all the dark matter subhalos that fell into the Milky Way's gravitational sphere across the history of the universe, most of them already consumed or dissolved, some of them still intact on distant orbits, some of them actively disrupting on closer ones, and a small number so far out and so recently arrived that the Milky Way's gravity has barely touched them yet, each one a faint world, each one an ancient structure, dark matter dominated, carrying a small population of old stars formed in an early universe, each one in its own time, beginning or continuing the slow gravitational drift toward absorption into a galaxy 1,000 times more massive. The drift is gentle, the time scale is immense. The outcome for most of them is already determined by the simple arithmetic of orbital energy and mass and time, worked out in the slow, patient calculus of gravity acting across distances no other force can cross. For now, the faintest of them sit at the edges of detectability, known by their statistical excess in photometric surveys, confirmed by the velocities of a few dozen individual stars, characterized by what they contain and by the enormous invisible structure that surrounds what can be seen. They are almost nothing. A few hundred stars in a dark matter halo, a slightly asymmetric scatter of old light in a field of equally old sky. And yet in that nearly invisible structure, the entire early history of the universe is quietly encoded, the epoch of reionization, the suppression of star formation in small halos, the mass scale below which galaxies could barely form, the particle physics of whatever dark matter turns out to be. All of it is there, carried in the slow orbital drift of a handful of ancient stars, waiting in the dark at the furthest, faintest edge of what can be seen, and just beyond it, in the deep population of satellites that the next great survey will, one by one, bring into the light. On a clear night in the southern hemisphere, far from any city, a person lying on their back in an open field can see two things that do not belong to the Milky Way's familiar arc. They glow softly against the dark, two detached patches of light, one larger and one smaller, hanging in the sky like pieces torn loose from the main river of stars and left to drift. They look close. They look like clouds. The larger of the two contains 3 billion solar masses of stars. Not 3 billion stars, 3 billion times the mass of the Sun, gathered into a galaxy of its own, with its own bar of older stars running through its center, its own spiral arms beginning to form, its own stellar nurseries glowing in deep red and blue, where gas is collapsing and new suns are lighting for the first time. It sits roughly 160,000 light-years from the center of the Milky Way, and it is falling. The fall is too slow to see across a human lifetime. It is too slow to measure across recorded history, but in the mathematics of gravity and motion, the trajectory is there, a long incoming arc, not a tight spiral wound down over billions of years, but something closer to a first approach, a body arriving from far outside the local neighborhood and curving inward toward a more massive center for the first time. The Large Magellanic Cloud is coming, and what lies at the end of that approach, across timescales longer than the Earth has yet existed, is transformation so complete that neither the cloud nor the galaxy it is falling toward will emerge unchanged. The smaller patch of light nearby is the Small Magellanic Cloud, a companion to the larger one, itself a galaxy of several 100 million solar masses, less organized in structure, its interior already disturbed by its long gravitational dance with its larger partner. The two have been close to each other in cosmic terms for a long time. They have passed near each other, pulled at each other, exchanged material. The evidence of that exchange is written not only in their shapes, but in the space between them, and in a vast ribbon of gas that trails behind them across more than half the sky. That ribbon is called the Magellanic Stream. It does not glow with starlight. It glows with radio emission, the characteristic signal of neutral hydrogen gas, cold and diffuse, spread thinly across a band of sky that spans more than 150 degrees from end to end. Mapped in radio wavelengths, it appears as a curving, attenuated thread, tracing the orbital arc of the clouds, and reaching far behind them, a wake left in the medium through which they move. The stream contains roughly 2 billion solar masses of gas, not a trivial amount. That is enough raw material to form hundreds of millions of stars, and it is already lost from the Magellanic System, already in the process of being claimed by the Milky Way's gravitational reach, already being drawn downward through the hot diffuse atmosphere of gas that surrounds the Milky Way at great distances. Two forces have worked together to pull the stream free of the clouds. One is tidal, the same differential gravity that acts across any extended body in a gravitational field, pulling harder on the near side than the far side, and in pulling, stretching the body along the axis of approach. Across the hundreds of thousands of light years that separate the clouds from the Milky Way's center, that difference in pull is enough to lift gas from the outer edges of the clouds and draw it into a long trailing structure. The other force is ram pressure, the pressure a body feels as it moves through a medium, the same principle that pushes against an open hand held out from a moving car. The Milky Way is surrounded by a diffuse halo of hot gas extending far beyond its visible disk, and as the Magellanic Clouds move through that medium, the gas of their outer atmospheres is swept backward, added to the stream, carried along behind them like a banner in a slow wind. The stream is not uniform. It has a head, called the leading arm, which curves ahead of the clouds in the direction of their motion, and a long trailing tail that stretches behind. The leading arm is already approaching the Milky Way's outer disk, and astronomers have found evidence that some of the gas in the leading arm is being absorbed into the disk right now, falling inward, adding mass and gas to a galaxy already built from such accretions. The stream as a whole has been forming for somewhere between 1 and 2 billion years, the accumulated result of repeated encounters with the Milky Way's gravitational and pressure environments. In that time, the clouds have given up an enormous fraction of their gaseous outer material. What is left, still bound within each cloud, is the denser, more tightly held interior, the stellar bodies and the concentrated gas that continues to form new stars. Star formation in the Large Magellanic Cloud is vigorous, in a region called the Tarantula Nebula, a stellar nursery so large that if it sat at the distance of the Orion Nebula, it would cast faint shadows on the ground at night. Hundreds of massive young stars burn at temperatures of tens of thousands of degrees, and the most massive among them are already near the ends of their lives, destined to end in supernovae within a few million years. The Large Magellanic Cloud is not a passive, fading remnant. It is alive with ongoing star birth, with the full activity of a galaxy doing what galaxies do, converting gas into stars, cycling material through stellar generations, building its stellar population year by year, even as its outer gas is being drawn away. This is part of what makes the Magellanic Clouds unusual among the Milky Way's known companions. Most of the Milky Way's satellite galaxies are small, old, and gas-poor, ancient systems that formed most of their stars early in the universe's history, and have been largely quiescent since, their star formation shut down by the heating of the intergalactic medium that followed the first billion years of cosmic history. The Magellanic Clouds are different. They are still rich in gas. They are still forming stars. They are large enough to have retained that gas against the pressures and tidal forces they have encountered, and they carry it now as they fall inward, carrying fuel for future star formation, not only within themselves, but potentially within the Milky Way, where the stream's gas may eventually rain down into the disk and ignite new stellar populations. The proper motions of the Magellanic Clouds, their actual angular motion across the sky, measurable with precise enough instruments, were first accurately determined using the Hubble Space Telescope, and later refined with the exceptional astrometric precision of the Gaia mission. What those measurements revealed was that the clouds are moving faster than previous estimates had suggested. Fast enough, in fact, that by some analyses, they are moving near or above the local escape velocity of the Milky Way, the speed at which an object would be able to escape the Milky Way's gravitational pull entirely and drift away into the wider local group. This finding has significant implications. It supports what astronomers call the first infall hypothesis, the idea that the Magellanic Clouds are not long-term companions of the Milky Way. satellites that have been orbiting close by for billions of years, but rather newcomers, arriving from much greater distances in the relatively recent cosmic past. Under this picture, the clouds spent most of their lives far from the Milky Way, orbiting each other and perhaps part of a larger structure, and only in the past few billion years have they entered the Milky Way's gravitational sphere of influence and begun the long inward arc that will end in absorption. They arrive carrying the memory of a different environment, richer in gas, more active in star formation, shaped more by their mutual gravitational relationship with each other than by their relationship with the Milky Way. The relationship between the two clouds themselves carries its own record of disruption. Between the large and small Magellanic Clouds, stretching across roughly 75,000 light-years of space, runs a structure called the Magellanic Bridge. It is a stream of gas and scattered stars, physically connecting the two galaxies, faint and broad, and traversed by a thin population of young stars that formed within it after the gas was pulled free. The bridge formed during a close encounter between the two clouds, approximately 200 million years ago, when the large Magellanic Cloud passed close enough to the small that tidal forces stripped gas from the small cloud's outer regions and deposited it in the space between them. That encounter left a mark not only in the bridge, but in the interior of the small Magellanic Cloud itself. The small cloud's internal kinematics, the pattern of how its stars and gas are moving relative to each other, are complex, more so than would be expected for an isolated, undisturbed dwarf galaxy. Some analyses suggest that the small cloud is not a single coherent structure, but two overlapping components, a foreground and a background population displaced along the line of sight, possibly the result of the cloud being pulled apart in depth by the gravitational interaction with its larger companion. The small Magellanic Cloud may, by some accounts, already be in the process of becoming two separate fragments, the internal disruption of a 200 million year old gravitational wound still working its way through the galaxy's structure, two galaxies pulling at each other, and a third pulling at both of them. The geometry of the Magellanic System is a nested set of gravitational influences, each acting on a different scale and at a different strength. The small cloud is deformed by the large. The large is massive enough, 100 to 200 billion solar masses when its dark matter halo is included, to exert a measurable gravitational pull on the Milky Way itself. Not on individual stars within the Milky Way, but on the Milky Way as a whole, on the position of the Milky Way's center of mass, and on the shape of the Milky Way's own dark matter halo. The Milky Way's dark matter halo is not a perfect sphere. No dark matter halo is. It is shaped by the gravitational influences that act upon it, by the history of mergers and accretions that built it over billions of years, and by the ongoing presence of massive satellites pulling at it from outside. The large Magellanic Cloud is massive enough to have displaced the Milky Way's dark matter halo from perfect symmetry, to have created a measurable wake in the dark matter distribution, a density enhancement, trailing behind the cloud as it moves, produced by the same gravitational dynamics that produce wakes in any medium when a massive body passes through. This wake, called the dynamical friction wake, has been predicted theoretically, and astronomers are now finding tentative observational signatures of it in the kinematics of stars in the Milky Way's outer halo. The large Magellanic Cloud is not merely falling into the Milky Way. It is, at its current mass, already reshaping the gravitational environment it is falling into. That mass will not remain unchanged. The large Magellanic Cloud is already losing material, gas to the stream, stars to the tidal field at the outskirts of its dark matter halo, and as it falls deeper into the Milky Way's gravitational environment, the stripping will accelerate. Each passage through the denser inner regions of the Milky Way's halo will remove more material, more gas, more stars from the cloud's outer layers, and the cloud will emerge from each passage slightly diminished, its mass reduced, its dark matter halo partially stripped away, its outer structure loosening and beginning to blur into the surrounding halo. The closest approach, the moment when the Large Magellanic Cloud reaches the minimum distance from the Milky Way's center that its current trajectory will carry it to, is predicted to occur in roughly 1 to 2 billion years. The numbers carry real uncertainty. The trajectory depends on precisely how massive both galaxies are, on the detailed shape of the Milky Way's dark matter halo, and on how much mass the cloud loses before it arrives. But the broad picture from numerical simulations is consistent. The Large Magellanic Cloud will reach a pericenter somewhere between 20,000 and 50,000 light-years from the galactic center, close enough that the tidal forces at that distance will begin to pull apart its stellar body in earnest. At that pericenter, the Milky Way's gravity at the Large Magellanic Cloud's location will be far stronger than it is today. The differential force across the cloud, the difference in gravitational pull between the cloud's near side and its far side, will be large enough to begin deforming the cloud's stellar bar and disk on timescales of hundreds of millions of years. Stars at the cloud's outer edges will begin to be drawn onto orbits that no longer follow the cloud's own center of gravity, but instead begin to trace paths around the Milky Way's center. The cloud will begin to come apart, not quickly, not all at once, but progressively, the way any extended structure comes apart under persistent differential force, its outer layers peeling away and dispersing while its dense inner core continues on for a time, a diminishing remnant, still coherent, still identifiable, still containing the brightest stellar nurseries and the densest concentrations of stars, until those too begin to lose cohesion and spread. The encounter will not leave the Milky Way unchanged, a body of the Large Magellanic Cloud's mass, even by the time of pericenter, after billions of years of stripping, likely still one of the most massive objects to interact closely with the Milky Way in recent cosmic history, will leave a wake in the stellar disk. Simulations suggest that the pericenter passage could trigger a burst of star formation in the Milky Way itself, as gas stripped from the cloud rains down into the Milky Way's outer disk, compressing existing gas clouds and igniting new stellar populations. The passage may also disturb the structure of the Milky Way's own outer disk, generating ripples and warps that persist for hundreds of millions of years afterward. What will not happen is a direct collision of stellar bodies. Stars are so small relative to the distances between them that even when two galaxies merge, individual stars almost never physically collide. What merges is the gravitational structure, the dark matter halos, the stellar streams, the overall mass distributions, and the stars that populate those structures find new orbits within the larger combined system. The Large Magellanic Cloud stars will not crash into Milky Way stars. They will drift among them, following orbits that curve through a gravitational field that was once their own galaxies and now belongs to the larger whole. They will mix slowly with the native halo population, settling over billions of years into a distribution that far in the future will be indistinguishable in position from the Milky Way's own stars. Only chemistry will preserve the record of their origin. Stars formed in the Large Magellanic Cloud carry the chemical signature of that galaxy's star formation history, a pattern of element, abundances set by the particular pace at which the cloud formed stars, the particular generations of supernovae that seeded its gas with heavy elements, the particular environment in which each star was born. Long after the spatial coherence of the cloud's remnant has dissolved into the Milky Way's halo, those chemical signatures will persist in the spectra of individual stars, faint but readable, the way a geologist reads the origin of a stone in the minerals it carries from a quarry long since covered over. The small Magellanic Cloud will follow a related trajectory, though its lower mass makes it more vulnerable, and its fate likely arrives sooner in the sequence. Already partially disrupted by its interaction with the large cloud 200 million years ago, already losing gas to the stream and to ram pressure as it moves through the Milky Way's outer atmosphere. The small cloud will be further disrupted by its proximity to the large cloud's own tidal influence during the infall, and by the increasing strength of the Milky Way's tidal field as both clouds descend into the inner halo. Whether the small cloud survives as a coherent structure through the large cloud's pericenter passage, or whether it has by then already dispersed into a stream of its own, is uncertain. What is clear is that the small cloud's mass, its stars, its gas, its dark matter, is also destined to become part of the Milky Way. The gas in the Magellanic Stream, which has already left the clouds and is already distributed across 150 degrees of sky, will arrive in the Milky Way's disk on a shorter timescale. Some fraction of it is already falling. Gas does not orbit as cleanly as stars. It loses energy through pressure interactions with the hot medium it moves through, and it tends to settle downward through the Milky Way's gaseous atmosphere, drawn by gravity toward the disk. When it arrives, compressed and cooling, it will form new stars, stars built from gas that was, 1 billion years ago, part of a different galaxy, a gas-rich irregular system that arrived from outside the local group and fell for hundreds of millions of years before its outer atmosphere was drawn away by forces it had never encountered before. There is something in the arithmetic of the Magellanic Stream worth staying with for a moment. 2 billion solar masses of gas that formed in the interiors of earlier stars, was expelled in stellar winds and supernovae, collected in molecular clouds, and was on the verge of collapsing into new stars before the tidal and pressure forces of the Milky Way's influence stripped it away and spread it across the sky in a ribbon too faint to see with the eye, but detectable with the right instruments as a continuous thread of radio emission stretching from one hemisphere of sky to the other. That gas carries within it the heavy elements made in the large and small Magellanic Cloud's own stellar generations: carbon, nitrogen, oxygen, the elements of organic chemistry. When it falls into the Milky Way's disk and forms new stars, those stars will carry within them the nuclear history of 2 other galaxies. The Tarantula Nebula in the large Magellanic Cloud, the enormous stellar nursery visible from the southern hemisphere as a faint reddish smudge within the cloud's glow, contains stars that are among the most massive known. Some of them exceed 100 solar masses, burning so brightly and so quickly that their lives will be measured in millions rather than billions of years. They will end in supernovae, and some of the most extreme may produce something stranger still, a collapse so rapid and so total that the remnant is not a neutron star but a black hole, and the collapse itself may release a burst of gamma radiation briefly, as luminous as billions of suns. All of this activity, the births, the short brilliant lives, the explosive deaths, is happening now in a galaxy that is falling, that is losing its outer envelope, that will one day be absorbed. The stars forming now in the large Magellanic Cloud are being born into a galaxy that will not exist in its current form 1 billion years from now, even as those same stars burn and live and die on timescales far shorter than the absorption that awaits their birthplace. There is no stillness in any of it. Even the gas trailing behind the clouds in the stream is not static. It is clumping, cooling in places, forming small concentrations that may be the seeds of new stars far from any galaxy's disk, in the intergalactic medium between the clouds and the Milky Way. Some fraction of the stream gas may never reach the Milky Way's disk at all. It may stall in the Milky Way's hot outer halo, reheated by interactions with that diffuse medium, held in a slow rain that never quite reaches the ground, not for billions of years, not before the next large gravitational disturbance reshuffles the system again. The infall of the Magellanic Clouds is not an isolated event in the Milky Way's history. The Milky Way has absorbed other galaxies before, left their stars in the halo as diffuse populations without spatial coherence, consumed their dark matter halos, and moved on. The Magellanic Clouds, with their combined mass, will be among the largest such absorptions in the recent history of the Milky Way. Perhaps the most significant galactic merger the Milky Way will undergo for billions of years to come, barring its eventual encounter with the Andromeda Galaxy far in the future. They arrive carrying gas, carrying stars still forming, carrying a shared history of mutual disruption, carrying the record of their own origins as independent galaxies in their chemical abundances and their orbital dynamics. The Milky Way receives them the way it has received everything else, not through any active process, not through any directed effort, but through the quiet, patient persistence of gravity, the same force that holds the planets to their orbits and the atmosphere to the ground and the galaxies in their slow dances across the void. Gravity does not hurry. It does not need to, given enough time, given the vast scaffolding of dark matter within which everything is embedded. The outcome is always the same. The smaller falls into the larger becomes the larger still, and the stars that were once the smaller galaxy drift slowly into new orbits, carry their old chemistry forward into a new gravitational home, and shine there, quietly, for billions of years more. On that clear night in the southern hemisphere, the two patches of light still hang above the field. They have been visible to human eyes since the first people looked up from those latitudes. They have been part of southern night skies for the entire span of recorded human history, and for the unrecorded millions of years before that. They will be there tomorrow night, and for millions of nights after. The timescale of their infall is so vast that it carries no urgency, no sense of motion or change across any span of time a person could live through or imagine living through. And yet the math is there, the trajectory is there, the stream is there, trailing behind them in radio light, tracing the path they have already traveled through the Milky Way's outer environment. The gas already falling from the stream's leading edge toward the Milky Way's disk is there. The gravitational wake already propagating through the Milky Way's dark matter halo is there, subtle but measurable, the signature of a large mass moving through a medium that responds. The absorption will take longer than the Earth has existed, longer than the Sun will exist in its current form. It belongs to a future so distant that no continuous thread of human concern can reach it. But in the longer accounting that the universe keeps, in the patient arithmetic of mass and gravity and orbital mechanics, and the slow mixing of stellar populations across billions of years, it is already underway. The Magellanic Clouds are already within the Milky Way's gravitational sphere. The gas is already leaving them. The orbits are already curving inward. Two small galaxies, bright enough to see with the eye, old enough to have formed their oldest stars when the universe was less than 2 billion years old, rich enough in gas to still be making new ones now, are in the long, slow process of becoming part of something larger. The stars they contain will not disappear. They will not go dark. They will be redistributed, carried along orbits that curve through a deeper gravitational well than the one in which they formed, settling over billions of years into a halo population whose origin in two other galaxies will be readable for a long time to come in the precise ratios of elements in their spectra. The southern sky above that field is very still. The stream spreads across it invisibly, 150 degrees of cold neutral hydrogen trailing behind its source galaxies, like the long, slow wake of something vast moving through deep water. The two bright patches hold their positions as they have held them every night within living memory, within historical memory, within the memory of any human who has stood under the southern sky and looked up. They are not going anywhere, not tonight. Not within any span of time that belongs to the world of days and seasons and human lives. But the math does not stop. Gravity does not rest. And slowly, in the patient dark, across timescales that have no human measure, the distance between the Magellanic Clouds and the Milky Way continues, imperceptibly, to close. In the data from a space telescope, among the recorded motions of more than 1 billion stars, there is a shape that has no visible edge. It is not a stream of light. It is not a cluster. It is a population of stars scattered across a wide volume of the Milky Way's outer halo, each one moving in an orbit that is long and radially stretched, diving deep toward the galaxy's center and pulling far back out again, the way a comet moves rather than a planet. Separately, each of those stars looks like any other halo star. Together, when their velocities are mapped all at once, they form a structure, a kind of crowd that moves in the same old style, in the same family of orbits, sharing a dynamic signature that points back to a single catastrophic event that happened 10 billion years ago, or more. The event was a collision, not a swift one, a billion-year unfolding of two galaxies drawing together, disrupting one another, the smaller one dissolving into the larger. What remains of it now is not matter in any concentrated form. What remains is the shape of how things move. This is how astronomers first recognized the Gaia-Enceladus merger, not by seeing the remnant galaxy, because no remnant galaxy remains, but by reading the motion record it left inside the Milky Way's own stellar halo. The Gaia mission, which began returning precise stellar data in 2016, measured the positions and velocities of stars in numbers that had no precedent. 1 billion stars. More, each one assigned a proper motion across the sky, a parallax distance, a line of sight velocity, where spectra were available. When researchers examined the halo population within that dataset, they found something that had always been there, hidden in the ordinary-looking distribution of stars around the galaxy. A large fraction of the inner halo is made of stars on radially elongated orbits, orbits that go deep and come back out, orbits that a star acquires when its parent galaxy falls directly into a larger one, and the infalling galaxy's own orbital energy converts into the individual star's radial motion as the structure dissolves. The shape of that motion is the fossil, and from the fossil, the event could be reconstructed, a galaxy of perhaps several 100 million solar masses, arriving from outside, merging with the Milky Way somewhere between 8 and 11 billion years ago, and in doing so, building much of what the interstellar halo is today. The halo that surrounds the Milky Way's disk is not smooth. It does not glow uniformly in every direction. Seen in the precise language of chemistry and kinematics, it is a layered archive, each layer the dissolved remnant of something that arrived from elsewhere and came apart over time. The stars of the halo carry their histories in their composition, in the ratios of elements forged in different generations of stellar explosion, in signatures that persist across the entire lifetime of a star and cannot be erased. A star born in a dwarf galaxy forms from gas that has been enriched differently than the gas inside a large spiral galaxy. Dwarf galaxies are smaller, their star formation is slower, their supernovae less frequent per unit time relative to the mass of iron already present in the gas. The result is a chemical fingerprint. The ratio of elements like magnesium and calcium, the so-called alpha elements, produced in the cores of massive stars and flung outward quickly in supernova explosions, to iron, which accumulates more slowly over time from a different class of explosion, is slightly but measurably lower in stars that formed in dwarf galaxies than in stars that formed within the Milky Way's own disk and early halo. That ratio is preserved in the star's spectrum, readable across tens of thousands of light years, as definitive as the orbit and just as patient. A single stellar spectrum is a narrow strip of light separated by wavelength, the continuous glow interrupted by dark lines where specific atoms have absorbed specific colors on the way out. The line of magnesium sits at one position, the line of iron sits at another. The ratio between the depths of those lines at a given overall metallicity tells the story of the gas from which the star condensed, how much stellar processing had already occurred, how many generations of massive stars had already lived and died before this one formed. In a Milky Way disk star of moderate metallicity, that ratio falls in one range. In a star born in a dwarf satellite, it falls slightly lower. The difference is not large. It is not visible to the eye. It is measured in the precise calibration of spectrographic instruments and encoded in survey catalogs that list the chemical abundances of hundreds of thousands of stars. But the difference is real, and it is consistent, and it repeats across every identified accreted population in the halo, each one with its own slightly different chemical signature, reflecting the slightly different star formation history of its birthplace galaxy. The halo, read this way, becomes a library, not a library of books, but of stars, each one a record of where it formed and when, of the gas conditions in a galaxy that may have dissolved 1 billion years before the sun was born. The large spectroscopic surveys that built this library, programs that observed hundreds of thousands of halo stars over many years, measuring detailed elemental abundances in each one, found that the halo is not a single population, but many, overlapping in space, distinguishable only in velocity and chemistry. Some populations are old and metal poor, born in tiny protogalactic fragments in the first few billion years of cosmic time. Others are more enriched, born in larger dwarf galaxies that had time to process multiple generations of stars before they fell into the Milky Way. The oldest and most metal poor are so thoroughly mixed into the halo that their spatial structure has been completely erased. Only their chemistry and the general shape of their orbital family remains. The somewhat younger ones, those that arrived more recently, within the last 5 or 6 billion years, still show spatial coherence in places, thin ribbons of stars, broad diffuse envelopes, arcs that wrap partway around the sky before fading into the background. Each of these structures is a galaxy in its final stage of absorption, its stars now living inside the body of the one that consumed it, orbiting forever in the deeper gravitational field of their new home, carrying the chemical memory of a place that is otherwise entirely gone. There is something steady in that image. The stars continue to shine. The light that left a star in the Milky Way's outer halo tonight, now part of a dissolved system, may have traveled for 60,000 light years before reaching a telescope. The star itself is old, perhaps 10 billion years old, perhaps more, and it formed in a galaxy that no longer exists in any recognizable form. Yet it shines. It fuses hydrogen in its core by the same physics that governs every other star. It will continue to do so for billions of years. The galaxy that made it is gone, and the galaxy that absorbed it continues, and the star sits inside that continuity, neither lost nor out of place, simply moved across cosmological time into a structure large enough to hold it without any further disruption, where it will orbit slowly and steadily until the last of its hydrogen is spent. The Milky Way's halo extends very far. The outermost measured stars orbit at distances several times greater than the diameter of the visible disk. Much of the mass in this extended region is dark matter, the invisible component whose gravitational influence holds the halo together and shapes the orbits of everything within it. When a satellite galaxy is absorbed, its own dark matter halo dissolves into this diffuse outer structure, contributing mass that never becomes visible, but that participates in the Milky Way's gravitational architecture for all time. The dark matter from 1,000 absorbed satellites, accumulated over 10 billion years, forms most of what the Milky Way's dark matter halo now is. The visible stars of the halo, those ancient dissolved remnants, those chemical fossils, are only a thin layer of light drifting through a structure built almost entirely from matter that cannot be seen. The halo is mostly dark. The record written in it is almost entirely invisible. And yet the record is there, patient and complete, waiting to be read by instruments precise enough to separate one star's orbit from another's, one star's chemistry from the background by a margin of parts per thousand. The question of how many galaxies the Milky Way has absorbed across its history has no clean answer yet. The oldest mergers, those that happened in the first 2 or 3 billion years, have had so long to phase mix, to have their spatial coherence erased by the differential orbital periods of different stars, that only their chemical signal remains. The more recent ones, those in the last few billion years, still have spatial structure. The streams are coherent. The arcs are visible in deep photometric surveys. Between the completely dissolved and the still recognizable lies a continuum, and surveys continue to trace it. The number of satellites the Milky Way currently possesses, those that have not yet been fully absorbed, grew from roughly a dozen known objects in the early 2000s to more than 60 confirmed or candidate systems by the mid-2020s. The increase driven entirely by deeper surveys covering more of the sky with greater sensitivity to faint, diffuse stellar populations. None of those surveys has finished. The full population of surviving companions is still not known. The forthcoming deep photometric survey, planned with the Vera, the 100th Rubin Observatory, is expected to find hundreds more, not because the sky is hiding dramatic objects, but because the instruments will be sensitive enough to detect the faint statistical overdensities that mark ultra-faint satellite galaxies, objects containing only a few hundred stars spread across many light years, invisible to shallower surveys, present all along in the data that was simply not deep enough to see them. Each discovery will add another name to the catalog of the Milky Way's companions and prey. Some of those objects will already be in the late stages of disruption, their stars beginning to spread into tidal tails. Others will be on their first approach, still largely intact, still holding their ancient populations of dark matter and old stars, beginning the long, slow process that will one day leave them dissolved and written into the halo in the same language as everything that came before them. Deep surveys of galaxies beyond the local group have revealed that the Milky Way's situation is ordinary. The Dragonfly survey and programs like it have imaged the outer halos of nearby galaxies in extraordinary detail, revealing systems of faint arcs, shells, and streams surrounding galaxies that in shallower imaging look unremarkable. Each arc is the remnant of a consumed satellite. Each shell is the spread out stars of a galaxy that fell in and came apart. The richness of these halo features varies from galaxy to galaxy, and the variation maps loosely onto the different merger histories that different galaxies have experienced. A galaxy that consumed many satellites over many billions of years has a complex structured halo, multiple overlapping streams, a thick envelope of accreted stars, a deep chemical archive. A galaxy that has had fewer mergers has a thinner, more uniform halo. The Milky Way falls somewhere in between, its halo structured and archival, its merger history moderately active compared to the range of galaxies observed. This is not unusual. In the cosmological model that accounts for these observations, all large galaxies grow this way. All of them are built in part from the dissolved remnants of smaller systems. The process that fills the Milky Way's halo with ancient chemical fossils is the same process that fills the halos of galaxies across the observable universe. Galactic cannibalism is not a local event or an edge case. It is how large galaxies become large. The cosmological model itself predicts this. In the standard picture of how structure forms across the universe, matter does not begin in smooth, uniform distributions. From the very earliest moments, quantum fluctuations laid down slight variations in density, and as the universe expanded and cooled, gravity amplified those variations. Dense regions drew in more matter. They grew. Smaller dense regions merged into larger ones. Larger ones drew in still more. The first structures to collapse were small, halos of dark matter and gas on scales that today would be called dwarf galaxies or smaller. These merged into larger halos, which merged into larger ones still. Every galaxy above a certain mass formed through this process of hierarchical assembly. The stars now in the Milky Way's halo are the luminous trace of that assembly, the debris of the building process, the leftover structure from a billion years of accretion encoded in chemistry and kinematics and preserved in cold, slow orbits far from the galaxy's center. The Milky Way itself is not finished assembling. The satellites it currently possesses are in various stages of the absorption process. Some are so close and so stretched that their tidal tails already span large fractions of the sky. Others are on long, wide orbits, making their closest approaches only once every few billion years, losing very little material per pass. The largest of the current companions, massive, gas-rich, still forming stars, have not yet made their first close approach. They are still falling inward on their first long arc, carrying their internal structure intact, their star formation ongoing, their dark matter halos still largely their own. In time, in the scale of time that the Milky Way measures in billions of years rather than millions, those companions will arrive. They will swing inward. The tidal forces will begin to work, and what is now a separate galaxy, visible to the naked eye as a detached patch of light in the southern sky, will slowly begin to give up its stars to the deeper pool of the Milky Way's halo. That process will not be fast. Nothing in galactic astronomy is fast. The orbital period of a satellite on a wide halo orbit is itself hundreds of millions of years. The full disruption of a galaxy, from first tidal distortion to complete dissolution, unfolds over timescales measured in multiple billions of years. The stars that are stripped earliest will complete many halo orbits before the last stars of the satellite are fully mixed into the background. For most of this time, the process is invisible to any individual observer. No human lifetime, no civilization's lifetime, spans enough time to see the configuration change. The streams that cross the sky look fixed. The satellites that orbit the Milky Way look stable. The absorption is real and ongoing and will not stop, but it moves in the deep time of gravity and orbital mechanics, indifferent to the scale at which life measures its days. There is a particular quality to this kind of time. It is not threatening. It is not rushing toward any particular end. It is simply the pace at which mass moves under gravity across the distances that define the Milky Way and its companions, hundreds of thousands of light years, orbital velocities of tens to hundreds of kilometers per second, crossing times of hundreds of millions of years. At these scales, even the most violent events are slow. A collision between two galaxies is not a crash in any ordinary sense. It is a passage, a close approach, a slow interpenetration of two gravitational fields, two populations of stars moving through one another without any individual stars colliding. The whole event playing out over hundreds of millions of years, from first contact to final merger. The stars continue to shine through the entire event. The physics continues undisturbed. The process is large and slow and utterly ordinary in the life of a galaxy. The Milky Way will not be consumed. It is the consumer in the transactions described across its halo. But the Milky Way is not the largest structure in its gravitational neighborhood, and the neighborhood itself is in motion. Andromeda, the large spiral galaxy nearest to the Milky Way, lies roughly 2.5 million light-years away, the most distant object visible to the naked eye from dark northern skies. A faint smear of light whose apparent smallness belies a stellar mass comparable to the Milky Way's own. Andromeda and the Milky Way are moving toward one another, not at the reckless speed of a collision in the ordinary sense, but steadily, gravitationally, the way all matter in a bound system eventually converges toward the common center. Within several billion years, the two galaxies will begin to interact. Their outer halos will overlap first, the dark matter distributions beginning to blend across a region of space defined not by light, but by the behavior of orbits. Then the stars of one halo will begin to interpenetrate the stars of the other. Then, over a much longer time, the galaxies themselves will pass through one another, each pass bringing them closer to a final merger that will assemble both of them, along with all their accreted satellites and all their merged dark matter halos, into a single larger elliptical remnant. That remnant will carry inside it the chemical records of everything both galaxies consumed across their histories. The halo fossils of the Milky Way's old mergers, including the Gaia Enceladus system, absorbed 10 billion years ago, will be present in the merged structure, as will the halo fossils of Andromeda's own merger history, which is at least as rich. The stars stripped from satellites of the Milky Way over the last few billion years, still coherent in streams and arcs today, will by then have had so long to phase mix that their spatial structure will be gone, but their chemistry will still be there, still readable in principle, still encoding the star formation conditions of dwarf galaxies that have been dissolved for 15 billion years. The archive does not close, it accumulates. Every merger adds a new layer of chemical and kinematic record to the halo of the final system, and that record endures for as long as the stars themselves endure, which is far longer than the timescale of any merger. This is the picture that emerges from the full record, from the precise kinematics of Gaia's billion-star catalog, from the chemical abundances measured in hundreds of thousands of spectra, from the deep images of halos in nearby galaxies, showing their full complement of streams and shells, from the cosmological simulations that reproduce the statistical properties of all of it. The Milky Way is a mid-sized spiral galaxy at a moderately late stage of its assembly. It has consumed many galaxies and is consuming several more. It holds in its halo a layered archive of every system it has absorbed, written in chemistry and orbital shape, fading from visible structure into chemical diffusion over billions of years, but never disappearing entirely. It is surrounded by surviving satellites in every stage from freshly infalling to nearly dissolved, and it is itself, on the scale of cosmic time, on its way toward a merger with the one system comparable to it in the local neighborhood, a merger that will carry forward the archive and add to it the way every merger before it has. The stars caught in this history did not know they were part of it. A star formed in a dwarf galaxy 10 billion years ago, in the earliest epochs of galaxy assembly, formed because a cloud of hydrogen and helium had reached the right density to collapse. It fused hydrogen in its core. It enriched the gas around it with heavier elements when it died. The galaxy it was part of went on forming stars for some time after. Then, that galaxy fell toward the Milky Way. The tidal forces stretched it. Stars from its outer regions began to trail away into long curving arcs. The galaxy grew smaller and less coherent. The stars that came from it, including the original star, if it was old and patient enough to still be burning, found themselves in new orbits around a more massive center. They continued to shine. They continue to shine now. Many of them are in the sky, above any observer in the northern or southern hemisphere, indistinguishable from native halo stars without spectrographic data, old and cold and steady, fusing hydrogen at a pace that will sustain them for billions of years to come. The stellar halo itself is thin. It contains only a small fraction of the Milky Way's total stellar mass, spread across a vast volume. If the disk of the Milky Way is a city seen from above, dense with light, the halo is the dark countryside surrounding it, sparse, quiet, the isolated lights of old stars, separated from one another by enormous distances of cold, nearly empty space. The halo is mostly dark matter and mostly nothing. The stars within it are widely spaced. The light reaching across that space is very faint, spread thin by distance, arriving at any given point at a level that would not be enough to cast a shadow. Between any two halo stars, the space is cold and empty and dark, save for the faint cosmic background that fills all of intergalactic space at a temperature only a few degrees above the lowest possible. This is the quiet interior of the archive. Still, old, patient, the fossils inside it do not require witness. They simply are. From any position in the Milky Way's halo, looking inward, the disk of the galaxy is bright. The bar at the center, the spiral arms fanning outward, the concentrated stellar density of the inner galaxy, all of this glows against the dark. Looking outward from the same position, the sky grows dim. The streams and arcs of the halo are not visible to the eye at those separations. They are statistical structures, real only in large data. But the individual halo stars are there, visible, resolved, each one a point of light in the long dark of the outer galaxy. Beyond them, very far, the other members of the local group. Beyond those, the first galaxy clusters. And beyond those, the large-scale structure of the universe, the same hierarchical distribution of matter that produced the Milky Way in the first place, still assembling, still accreting, still building larger and larger structures from smaller ones over timescales that dwarf even the age of the galaxy itself. The The process that fills the Milky Way's halo with ancient stellar fossils is a local expression of something universal and very old. It began in the first structures to form in the universe, when the first dark matter halos assembled and drew in the first gas and lit the first stars. It has continued without pause since then. It will continue for longer than the current age of the universe, before the largest structures finish assembling and the cosmos begins its long, slow approach to equilibrium. The Milky Way is one step in that process. Its absorbed satellites are one contribution to the total census of hierarchical assembly. The streams in its halo are the same kind of feature that appears in halo surveys of galaxies across the observable universe. The universal signature of accretion, repeated at every scale, in every environment, in every epoch of cosmic history since the first structures lit. There is nothing in the halo of the Milky Way that requires anything unusual to explain. No special conditions, no outlier events. The accretion record in the stellar halo follows from the same physics that governs matter everywhere. Gravity drawing mass together, tidal forces stretching smaller structures within larger gravitational fields, orbital mechanics preserving the kinematic signatures of past events for billions of years before phase mixing finally erases the spatial structure and leaves only the chemical record. The record persists. The stars persist. They continue their slow orbits through the outer reaches of the galaxy, cold and ancient and entirely unchanged in their physics from the stars in the disk and the bulge and every other structure in the universe. They carry in their spectra the conditions of their birth, and those conditions point back through billions of years to galaxies that no longer exist, to the dense early universe where those galaxies formed from the same quantum fluctuations that seeded everything that has ever been made of matter. A halo star on a long radial orbit swings inward toward the galaxy's center and then back out over and over on a timescale of hundreds of millions of years per crossing.